As usual, go ahead and start the scientific part of the day. So Dr. Erin Kado-Fong is going to talk about tiling, stacking, and difference imaging, and I'll let her introduce herself.
Okay. Thanks very much. I'm very proud of all of you for somehow making it back from the taco stand in a prompt manner. So my first lecture is going to be about stacking, tiling, and difference imaging. But before we get into that, I'm actually going to give you a very quick spiel about myself. And I added these slides in right before lunch. The reason being, I wanted to get a coffee this morning. And so I walked down to the aquarium because it's the only place open. And I asked the guy outside, like, oh, can I just go in and get a coffee really quick, thinking that, you know, the cafe is in the lobby and stuff. He's like, sure. You're like, you don't need to get a ticket. And then he just lets me loose in the whole aquarium. And that's what I learned. Like, if you wear a name tag and ask nicely, you can get in anywhere. So I want to convince you that I am not a biologist who's just come in from the aquarium. So I'm going to give you a really quick overview of what I think about scientifically. So I am a postdoc at Stanford, and I think mostly about using large wide field imaging surveys to understand baryonic processes in low mass galaxies. When I say low mass galaxy, I mean anything less than around 10% the mass of the Milky Way.
I'm very sorry to interrupt. Can you just click the OK right there so we can read your titles? It's just on the sorry for the interruption.
So I mean galaxies up to around the mass of the LMC. Historically, we thought of these dwarf galaxies as having a lot of potential as precise probes of dark matter and trying to unveil the nature, the particle nature of what dark matter really is. There's a very substantial roadblock in actually using these types of galaxies as the precise probes that we think they could be, which is that we don't understand the baryonic processes that go in them, at least not in a complete or very quantitative way. So I think about baryonic processes, so star formation, AGN feedback, supernova feedback in low mass galaxies on different scales, going from kind of subgalactic scale, star formation, baryonic cycling, all the way up to kind of galaxy halo assembly in a high level of the universe. The reason why this is relevant for this section on wide field imaging is because to do this type of work, I think a lot about galaxies and subgalactic structure and extended source photometry, especially in these large format, kind of large volume surveys. So that could be things like looking at star formation efficiency in nearby galaxies. It could be measuring surface brightness profiles to try to infer the three-dimensional intrinsic shapes of galaxies from their ensemble of two-dimensional shapes. It can also be looking at very low surface brightness tidal debris that's been cast off from interactions between galaxies. So that's just my little spiel to convince you that I am not a biologist. But today we're going to be talking about tiling, stacking, and difference imaging. So I know that you've got a lot of pedagogical lectures, so you might have seen this before. This is called Bloom's taxonomy. This is an abbreviated version, but it's basically the idea that there's different parts of learning and different kind of, or a hierarchy of going from, you know, remembering and understanding concepts to creating new work. So in broad strokes, our goals for the lecture today are to understand what stacking, tiling, and difference imaging are. So what are they, the concepts definitionally, why would we want to do them? Then we can go up a level and ask how are coads, which I'll get to in a second, and difference images actually made with astronomical data? What are the pitfalls? What are the kind of strategies that we think about to make these types of images? Then how do we design surveys to optimize for different and diverse science goals? So especially as we go into this kind of LSST era, there's very large collaborations with a very large array of science goals, and not everybody can do the same science. Not everybody's science is optimized for any given strategy. And this does kind of relate to how we think about doing coads and difference imaging. And then finally, we'll go into the create set with the create step with the problem set. Okay, but let's start at the bottom of the pyramid. So the anatomy of an exposure. So let's say that this is an exposure and we have a grid of pixels that is of shape n by m, and this is a single frame exposure. So it's from the telescope, we get pixel intensities. Each pixel registers a value that's related to the number of incident photons. So you've seen this earlier this week. I think it was Monday's lecture on CCDs. So each exposure is going to have a value for each pixel that tells you something about how many photons were incident. Now, though, we're going to consider a stack of D exposures. So we're going from this n by m array to an n by m by d, where d is the total number of exposures you have in the stack. And now, instead of a single pixel value, Pij, each pixel position is going to have a vector of values. So a vector of length d that's going to describe the photons seen by that pixel over the set of exposures at position ij. So, because I don't want to sage on a stage to you for an hour, which is a term I learned this morning. First, let me just check, is anybody in a row where they don't have a partner to discuss with? And if so, can you move up? If everybody's good, then we could just skip that, but I just wanted to make sure that everybody has somebody to talk to. So you learned about CCD lecture or CCD and detectors and exposures in an earlier lecture this week. So if we want to go deeper on a source, one thing that we can do is expose for a longer time, right? As we have a longer exposure time, we should collect more pixels or more photons from the source. So from what you learned in earlier lectures, what prevents us from just taking very long exposures? There's a lot of answers to this question, just to give you a heads up. But if you want to just take, let's say, 30 seconds to discuss with the person next to you and think of a list of reasons why we might not just take a longer exposure.
Yeah. Contaminants you'll have. Yeah, but not just cosmic rays, but also all the right. Yeah, all of the but also like what are we looking at that also changes with time? Yeah, might be changing from time. Right. Yeah. Or even moving. It's like, I mean, I know we can guide and track really well, but I'm sure it's easier to track for a small chunk than like make it track. Yeah. Maybe. Yeah. What do you expect? Would you? Yeah, I guess I'm thinking about like, does the background amount go up the same amount as the source amount? And I think it does. In your way, it gets easier with time. Is that true? I would think so. Do you not think so? Because like, or is it like one time big? Yeah, yeah. No, I mean, I think what you described makes sense to me. Like, it should build up.
Okay. Okay, maybe not the background. You're all having such great conversations that I'm almost sad to interrupt. But we do have more discussion questions later, so I do want to keep going on. But does anybody want to report back from the brief discussion with their partner, some of the things that they talked about? Yeah.
The longer you expose, the more cosmic rays will hit your detector.
Yeah, that's a great one. So the longer you expose, you have these charged particles that might hit the detector. We don't want to measure cosmic rays, we want to measure astrophysical sources. And at some point, you'll just see cosmic rays. What else? Yeah?
Sources might change.
Yeah, that's great. So there's astrophysical variation in sources that we also want to measure. If we just expose for 10 hours, we're going to essentially integrate over a lot of that change. Yeah.
You might saturate if you have too many electrons in the pixel.
Yeah, that's great. So I'm not sure if you already went over saturation in CCDs. Everybody's nodding. Okay, yes, that's a great example. So we're eventually going to saturate the brighter sources. Yeah, in the back. Yes, exactly. So there's both astrophysical variation and brightness. There's also astrophysical variation in the reference frame. So we have to track the sky, and as we create for longer, that becomes more difficult. So these are all really great. And essentially what I have written down here, you also have some system drift in your detectors themselves and kind of thermal drift. So there's a lot of reasons why we might want to take a series of shorter exposures and average them together rather than taking one kind of ginormous exposure. And when we take a series of exposures, so when we go from a stack of exposures to our averaged final image, that's called a coad. So from a stack of exposures, we want to obtain a co-added image from the single frame visits. So here's an example of 2 single frame images. One thing that I forgot to mention also is that a great thing about co-adding is that you can average over the chip gaps. So there's these chip gaps between CCDs. You can see them as these kind of white rectangles here, which is just the actual physical distance between the CCDs. We can't measure what the CCDs don't see. So when we take a series of images and co-add them, instead of taking one very long exposure, that lets us average over the chip gaps. So the goals of co-addition, we want to maximize the image signal to noise ratio. So we'd like to obtain the deepest possible image that we can from the stack of single frame exposures. What deepest actually means can actually vary a little bit from science case to science case, which I'll mention in a little bit. We also want to remove and reject imaging artifacts. So like you said, cosmic rays, we'd like to remove these kinds of things that we don't want to see in our image. Having multiple images is a great way to do that, because we can say, well, there's this really long linear feature in this single frame exposure, and it's not there at all in the other one, so it's probably cosmic ray. And like I said, we want to be able to construct contiguous survey imaging. So both averaging over chip gaps and building up this larger survey area, contiguous survey area. And like I mentioned, optimal co-addition methods can't vary in science case, which I'll mention again in a little bit. And I'll just say that these particular single frame images came from the Hedris Prime Cam on Subaru, which is an 8.2 meter telescope. So what do co-eds actually look like? So this is an example again from HSC. So at the left here, we're showing 2 single frame images. At the right, we're showing the eventual co-add. And a couple things can pop out immediately. So first, you don't see the chip gaps anymore, which is good. We're filling in the coverage. And then 2, if you look a little bit closer, there's a lot more sources that we can see in the co-added image compared to the single frame visits. Yeah.
I thought we'd still be able to see a strip because we're averaging 0.
Yeah, that's a really good point. These aren't the only 2 images that are going in the co-ed. Thank you for bringing that up, because yes, if these are the only 2, you would expect to see probably like a rectangle here or something like that. Yeah. Right, so you can also get substantially deeper in the co-eds relative to your single frame images. So you can see a lot of these fainter sources popping out, which is really important when we want to detect very faint stars or very faint galaxies. Okay. So we talked about why we care about co-ads, like why we want to make co-ads now. How do we actually go about making co-added frames? So there's really 4 steps. The first is to convert all of our single frame images to the same on-sky geometry. The second is to map all of our single frame images, and I will go through these steps in detail, by the way. This is just the roadmap. Second is to map all of our single frame images to the same flux scale, which I'll explain later. And then the third is to stack images to create co-ads. And the 4th kind of extra step now is to distribute the co-ads to the scientific public. So I want to take a really quick poll. Would you guys prefer that I ask you questions individually and have you raise your hands, or that you can discuss with your partner first before we go through these discussion questions? Can you raise your hand if you prefer discussing with a partner first? Oh, it's like, wait, can you raise your hand if you prefer just individual questions? Raise your hand. I think it's narrowly for partner discussion first. So we can do a mix, but for this one, why don't you discuss with your partner for a minute or so? If you think about these different steps, what are some potential technical hurdles that you might encounter with making co-ads? So things like, how do you get things to the same geometry, map things to the same flux scale, stack images? If you don't, if you feel like you don't have enough background to really say, that's totally okay. What we're trying to do right now is just to build a framework for asking questions in the right direction, not necessarily knowing the answers. So I just want to make that clear. So why don't you discuss with your partner for about a minute?
But the idea that came to mind for me at first was putting them on the same geometry, but she already lists that, so I assumed she meant something else.
I mean, these are the hurdles.
That's what I thought too. Yeah. Yeah, I guess so. I'm part of a collaboration that deals with issues like this a lot. Not me, luckily. I don't have to deal with the co-ed procedure, but like for us, one big problem is we're co-adding a lot of images. So we've automated this process, but what that means is that we don't look at each of them that are going into it. So oftentimes you'll add them up, you'll like send off the command to add up like a month's worth of data, and you get it back and it looks crappy, and you have to figure out why, and that involves like digging into like the individual images.
What is usually the case?
Normally it's just like there's some exposure where it's like, oh, the telescope was pointing at a wall and it just like snuck through, or it was like particularly bad like seeing like that one night. And
Those are the hurdles.
yeah, exactly. Like figuring out how to filter that out, I guess. But I think in this instance, if you're looking at them, you would know.
Yeah, and also like if you already have the same flux scale, you cannot have the same flux scale
Yeah,
or
that's
the same. Yeah, I guess same flux scale. I'm also just taking the co-edited ones already, so
Do you ever see anything weird in that?
I don't see the images. I look at spectra, spectra,
Yeah.
but yeah.
What are the normal problems?
I don't think so. Actually, when I see a co-edit one, I usually need to go through night by night to see if I had any change, because that's what I like. I want to see some type of
Okay,
change
just making
because
sure there's not variability.
yeah.
Yeah.
But I don't know. Maybe that gets like lost in the co-edit one. That's not the hurdle.
Yeah,
to
yeah,
me,
yeah,
to
yeah.
co-ed. That's just- So I don't know what they go through.
I'm not sure either. I mean, I guess it's like probably it all gets wrapped up in like how exactly you're stacking.
The thing that we're good at, yeah, are all of this, and they're all having a big back. Oh, no, they're separate. Okay, so you might take it. For you. Okay, it seems like conversations are wrapping up, so let's come back together now. So why don't we start from the top? Okay, so why don't we start from the top and hear from a few different groups? So first, converting all of our single frame images to the same geometry. We have a lot of exposures taken close to the same location. Did anybody discuss problems that might come with trying to work all of these exposures onto the same pixel order? Yeah.
Something that we deal with in radio is non-Gaussian noise.
Yeah.
And so if you're looking at any point outside of the phase, then you can do some like new transients, with like constructive interference between the different fringes.
Yeah, that's a great one. So specifically in radio astronomy, when you're looking at different parts of your effective field of view, you can't always work immediately to the same location. You can introduce kind of second order effects from correlations between the original detectors. Yeah.
Because the telescope has a finite mirror size, the pixels are exactly matched. So like if you're trying to map something, a set of pixels that are near the edge of your detector to one that's in the middle of another of a different frame, then you have to make sure that they're working correctly is that they actually want to know.
Yeah, that's great. So there could be variations across your field of view in terms of your geometry. So kind of a similar problem between optical and radio that we encounter across different wavelengths. What about flux calibrating your images? So making sure that a count of 20 in this exposure means the same thing as a count of 20 in the other exposure. Did anybody discuss that? Yeah, at the back.
Yeah, we just talked about it. That's like a potential hurdle.
Yeah.
I wouldn't expect that would be like the same.
Yeah, so it's a clear kind of potential roadblock here. When we look at the sky with different observing conditions, how do we know that we're seeing the same thing, or how do we get everything onto the same scale? So it's a great question to ask. I think I saw somebody in the frontish. Yeah.
Yeah, no, we were just talking about variability of sources as well, especially if you're looking at transients.
Yeah.
You know, they might be there, like they might have like a certain flux value in one scan. By the time you're at the next scan, the flux is considerably decreased or increased. So, and also because you're dealing with positional uncertainty at that time as well, can't really, sometimes it's very difficult to make a judgment where you can say that these are the same source you're looking at across two different images in the stack.
Yeah, that's a great point. If you're trying to measure variability itself, astrophysical variability, and then you also have observational variability, maybe the atmosphere changes, maybe the conditions are a little bit different. Maybe you come back to the telescope and the detector behaves a little bit differently. How do you separate out the variability that you care about and the variability that you don't want to see? What about stacking and co-adding the images themselves? Did anybody discuss that? Yeah.
So this kind of is related to both the first and the fourth point. Like if you're trying to stack multiple images and you have so to align them, you would have to find, okay, I have done is align the brightest pixel and find the position, but in some cases they are spatially extended. So you cannot find like exactly where, which pixel to align and which set of pixels to align. So in spatially extended cases, it's hard to, if the spatially extended one is the brightest one, it's hard to align.
Yeah, that's a great point. So if I'm making a coad, for example, and I introduce a little bit of positional error in the coad, then I could create a pretty big halo around something that doesn't actually have one. When I say halo, I mean like this extended diffuse light. And I could create a halo around an image that doesn't actually have one. I could overzealously background subtract and create a kind of dip around very bright galaxies. Did anybody else talk specifically about co-adding processes?
Yeah, you're talking about the, like, if you mess up your astrometry, you can like completely have like a source that's in like one exposure that's like completely shifted, and like everything will be shifted off in some direction.
Yeah, definitely. So you can also have astrometric errors, and suddenly you'll have a little dipole in all of your sources, and you'll say, oh my gosh, all the galaxies are brighter on one side and they're negative on the other. And of course, that's not what you necessarily want in the end. And then the last part, which I think is becoming increasingly more of a roadblock for surveys as they get larger, as surveys think about distributing their full data sets to the public, is actually how you get coads out to the scientific public. So did anybody talk about this in their groups? Okay, yeah.
When you're just distributing a single image, you can typically just provide like the very base, like I looked at this coordinate for this amount of time at this band, and at this time, and that more or less covers what someone would need to use that data. Whereas if you talk about the coads, you have to be very explicit about not only that part for all the images that are there, but you also have to be very clear as to how they were stacked. In that way, and then also make sure that it is still in a usable way, which may not necessarily be here, or useful in a transportable way, which may not necessarily be from.
Yeah, that's a great point. So as we distribute images that are more processed, we need to make sure that the user community understands how they were processed, because it's very important in using these images for science. Did anybody else talk about distributing coads as part of the roadblock or the roadmap to coad generation? This seems to have been the least popular aspect of coad generation. So I'm going to go ahead a lot of the things that I put up are much simpler than what you all discussed, which is great. So things of on-sky geometry, also the sky frame's not Euclidean, it's on a sphere, which makes you make choices about how you project things into 2 dimensions. We also need to think about pixel resampling. So when we convert and warp all of our single frame images onto the same geometry, we have to resample their pixels, and that requires interpolation, which is also choices. Flux calibration, we really talked about everything that I think I put up here. So images are taken under different conditions. We need to identify calibrating sources, which I'll talk about in a little bit. Stacking images, so how to optimize for different quality images, time variable artifacts. And then one thing that I want to add about distributing COADs to the scientific public, which I think will be very important for everybody who is either making a survey to distribute to the public, or the scientific public, or the users of a public survey, like LSST, like what many of the new flagship surveys will be, like SDSS already is, like HSC already is, like DECAM and the legacy surveys, or DES and legacy surveys already are, is accessibility and data set size. So back in before, data set size was not as much of a problem when you're thinking about distributing surveys. Sometimes you could put everything on a hard drive and just say, okay, I'll mail it to you. And that is really not the case now in this era of kind of big data astronomy. So there has to be a lot of thought put into how you're going to host the data, how you're going to make it accessible to the user community, and how you're going to make it accessible, not just how they can get the data, how they can actually get the values of the pixels, but how do you enable users to use your COADs responsibly? So that's exactly what you were saying. As images become more processed, it becomes more complicated to use them in a scientifically responsible manner. And one of the big parts of COAD distribution that I think is still not 100% solved is what is the best way to communicate to this large community how these COADs were generated and how you should go about using them. What are the caveats and the ways that the background was subtracted, the flux was calibrated, the geometry was all done? And how do you tell the public that's using this for a lot of different science cases when they can or cannot use these pixels for a certain thing? So here's our roadmap. We talked a little bit about the roadblocks that you might have in making the COADs. So let's jump into the actual steps now. So first, we want to convert all of our single frame images to the same on-sky geometry. So single frame exposures don't natively have the same mapping between pixels and real world coordinates. So if you think back to our example with the single frame exposures from HSC, you saw that the chip gaps, so those white rectangles, weren't oriented in the same way from one or another. And that means, well, that's an indication rather, that your mapping between the pixels and the real world, so RA and DEC, is not going to be the same between these 2 exposures. So you need to warp between what you see in the single frames and what you want your stack or COAD geometry to be. We can use the positions of known sources to orient each exposure. So this is something that was covered to some extent in yesterday's astrometry lecture, I believe. Are people nodding? Yes, okay. And then each exposure must be warped to a unified pixel coordinate space in order to create our image stack and eventually our COAD. And like we already discussed, this itself, or identifying these calibrating sources themselves, can also be a challenge because first of all, you need to know exactly where they are. Second of all, you don't want to choose anything that's actually moving relative to us, right? You don't want to have a moving reference frame. So this allows us to warp our single frames onto the same geometry. So we identify these sources, we warp them onto the same pixel geometry. And that takes care of the geometric component. But then we also want to map all of our single frame exposures to the same flux scale. So luminosity is the intrinsic source brightness, so ergs per second. Flux is our observed source brightness at Earth, so ergs per second per centimeter squared. Flux is the ratio between luminosity and 4 pi times the luminosity distance squared. if you're not working on cosmologically significant distances, this is just the distance. Once you get out very far, the luminosity distance becomes a little bit more complicated, but I'm just going to leave it there, that it is related to the flux in this manner. We also have a photometric filter. So when we look at through a CCD, or when we look at CCD images, we're looking through some bandpass. And our filter allows us to observe a specific spectral flux averaged over a known bandpass. Here is an equation that looks more complicated than it is for the magnitude seen in a specific bandpass. I'm going to break it down like so. So the specific spectral flux is here, which is just the flux, the derivative of the flux with respect to wavelength, or it could be respect to frequency. And then the Tx of lambda here is your filter transmission curve. So what this is really saying is that your magnitude is proportional to negative 2.5 times the logarithm of the ratio between the flux that you see averaged over your transmission curve and the flux of some calibrating reference source, which for the AV magnitude system is just a scalar for specific spectral flux in frequency space. However, the complication is that there's changes in observing conditions. So changes in observing conditions affect how many photons will actually hit the CCD. And you don't want to be measuring what the atmosphere is doing. You want to be measuring what your astrophysical sources are doing. So we want to correct for that. There can also be things like detector drift. Sometimes you have hot pixels, which you may have talked about earlier this week. So some of the pixels may be more or less sensitive. They might always register a high value. We want to correct for all of that. So the way we do that is by, again, going back to our reference catalog. So observations are taken under different conditions and detected properties may vary with time. So we're going to go back to our reference catalog and say, okay, I know where these three sources are. Now I've warped everything to the same geometry, so I know where they are in my co-ed pixel space as well. And I know how bright they should be. So I can see how bright they appear to be in each of my single frame exposures and correct or calibrate the flux scale of those single frame exposures based off of how bright I know some of these reference sources to be. And that allows me to then infer how bright these unknown non-reference sources are. So this brings us up to now we have a set of stack of exposures where they all have the same geometry. We know what the flux scale is. So then let's think a little bit about stacking images to create the coads and an aside on artifacts. So we've already, yeah.
I'm sorry, before we move on to step three, just had a question about the flux and backpass calibrators. Do they have to be in these? Do they have to be in the same field as your target for observation?
Yeah, that's a great question. You generally want them to be as close as possible because you can also expect one variation between CCDs and some field of view variation. So ideally, you would want all of your calibrating sources to just be in a nice grid that's very evenly spaced and close together. That's of course not exactly what we have in real life, but we can interpolate over our reference sources to try to get this kind of spatially variant flux calibration.
And what kind of, so I assume it's all point sources, but like, is it generally most of the calibrators that you use are stars, or are they like quasi-stellar objects?
Yeah, you generally want to use stars. The caveat to that is you want something that's stable in brightness over time. So for example, you could theoretically choose a variable star and then get very strange flux calibrations because your star itself is changing brightness as a function of time. AGN also have this kind of long, like hundreds of days random walk type light curves. But yes, generally stars. Okay. So now we have our flux calibrated exposures and they're all in the same geometry. So we're ready to make our coeds and get really deep into the night sky, except we also have a lot of artifacts in some of these exposures. There's a few different ways to take care of artifacts, and there's really, just talking about astrophysical artifacts could fill at least an hour, probably more, just to kind of scratch the surface. So I'm not going to tell you about all of the different artifacts and ghosts and ghouls and cosmic rays. but I'm just going to give you a general idea of how we remove artifacts, and then one specific example with cosmic rays. So non-astrophysical artifacts are very common. So you can have things like cosmic rays, so charged particles hitting the detector. You can also have things that are truly, in the night sky, like satellite trails, where yes, they are something that the telescope is actually seeing that is in the sky, but we don't care about it. We don't want to track it. You can also have optical phenomena from the detector, or sorry, not from the detector, from the telescope itself. So things like optical ghosts, scattered light from bright stars, diffraction spikes, etc. What all of these things have in common is that we don't want them in our final co-ed. So here I'm just showing a schematic of maybe we have 4 single frame exposures, and we've got this one cosmic ray in the 3rd exposure. The good thing about these types of transient artifacts are that we can remove them from kind of spot the difference algorithms. So we see nothing here, a huge feature here, and then nothing here again. That gives us the clue that we probably don't want that huge linear feature in our final co-ed. One caveat to this is that we want to keep all of the co-addition operations linear to preserve the PSF. What I mean by that is that you don't want a co-addition function that is something that depends on the data in the pixels itself, because that means that your PSF will change as a function of what the input exposure images are doing. So to give you an example of this, you could think about trying to take out these cosmic rays or these linear artifacts that are very bright through iterative sigma clipping. And what that means is that you look at the distribution of pixels, you say this one's super bright compared to the other exposures, I'll throw out this pixel. The problem with that is that you can also start to throw out the cores of very bright stars or something that's varying as a function of time. And that means that your point spread function, your effective way that the light spreads from a point source, which you talked about earlier this week, will change for the brightest stars in your image relative to your fainter stars. That's not a property that you want in your co-eds. So you want to keep these operations linear, not dependent on the data and the pixels themselves. So that's good if you have a lot of images to co-ed over, but sometimes you only have a few exposures or even just one exposure. One other thing that we can do is use morphology to flag artifacts, and we're going to look at this more quantitatively in the problem set. But essentially, in the case specifically of cosmic rays hit the detector and excite electrons, creating a characteristic thin linear pattern like this. And one thing that we can do is use the kind of impossible thinness of these features. They're much thinner than the point spread function, which means they can't have been going through the atmosphere the whole setup to flag these cosmic ray features. And you'll actually see this in the problem set because we'll do a simplified version of the LSST cosmic ray detection algorithm. Okay, so now that we've mapped everything to the same geometry, we've got everything on the same flex scale, and we've gotten rid of our artifacts, at least to the best of our ability, we can finally stack our images to create co-eds. And what this means is we are going to apply some averaging function to go from this vector P at position I, J to a single pixel value in your co-ed at the same position. And in the simplest case, this is where all of your exposures have the same noise properties. One thing that we can do is use a mean stack. So this is just taking the mean over all of the exposures, and that will be your final co-ed value. How you co-ed actually also matters. So this is mean co-addition, what I just described. This is great when all of your exposures are exactly the same, they have the same noise properties. But you can also do inverse variance weighted co-addition. This is when you have some exposures that were taken under great conditions and some exposures that were taken under not so great conditions. You want the exposures that were taken under good conditions to mean more for the stack than the ones that were taken under bad conditions. One way to achieve this is inverse variance weighting. That's what you'll do in the problem set. For point source detection, we can also do full with half max weighting. So this is very similar to inverse variance weighting, but essentially you're going to upweight things that were taken under very good seeing conditions, so very high resolution, downweight things where the light is really spread out. But I just wanted to flag this as something that we'll look at more closely in the problem set. So this is how we make a coed. At the end of all of these steps, you're going to have a much deeper image than any of your single frame exposures, and you'll be able to map out large contiguous areas of the sky. Yeah.
We're doing co-adding instead of long exposure, but a long exposure wouldn't that be the same as just adding these, not taking the average of these?
Yeah, so it would be the same with the caveats of why we don't want to simply take long exposure, but also when you flux calibrate your really long single exposure, you'll get back to the same flux scale. So you don't want necessarily to say you don't want the brightness of your sources to be correlated with how long you exposed, right? Because you want to know how bright they are, either intrinsically or as you promote. But that's a great question, yeah, because if you just take the counts, they'll go up as you expose them. Okay, so now we've created a coed. We've talked a lot about when things change. This is called difference imaging. And we often think of astronomy as happening on timescales long compared to human timescales. Like, for example, I think about galaxy evolution and star formation in galaxies. And often when we say things are almost instantaneous, we actually mean like a million years. So we often think about, or at least I often think about astronomy as happening on very long timescales. But there's lots of interesting astrophysical phenomena that happen on timescales that are very similar to kind of human observation timescales. So these can be transient, they can be stochastic, they can be periodic. In the periodic camp, you can think about things like eclipsing binaries of stars. So when you have a binary stellar system and you're in the line of sight of the orbit, sometimes you'll have one star in front of the other, sometimes you'll see both stars, sometimes you'll have the second companion in front of the first, and that creates this variation in light curve. So you're either seeing the brightness of both stars, just the brightness of one. You can also think of these pulsating variable stars. On the extragalactic side, blazars, quasars, AGN, young stellar objects, well, I guess it's not. Well, and the AGN side, blazars, quasars, and general AGN, we also see variation on long timescales, and then also transient events. So not things that are varying kind of over time or pulsating, but more events that you don't see, then you see, and then it decays. So supernova, superluminous supernova, etc. This is really just to say that there's a lot of interesting astrophysics to be done on human timescales as well. So how do we know if something has changed in an image? We've talked quite a bit about things that change, either when we're interested astrophysically in how brightness or position is changing, artifacts that are time variable, but how do we know quantitatively whether something in an image is the same or is different? And the answer is called difference imaging. So here is the science frame, and we'd like to know if anything in this field of view has changed. This is probably a leading slide because I wouldn't show this particular image if nothing has changed. That would be a very strange choice for a difference imaging lecture. But we can also look at a reference coed. So this is an image made using all of the same coaddition steps that we talked about earlier, but over a previous time period. And now we can see very clearly that there is a source here that didn't used to be there in the past. And then you can create a difference image, which is essentially the difference between these two. And now your time variable source pops up very nicely, or in this case, a transient source. This is a supernova. Now, we talked about a roadmap to coads. Now let's talk about a roadmap to difference imaging. I'm going to skip the discussion part because we're running low on time. But essentially, we want to create a reference image. So this will have all of the same things as when we did our coad. And then we want to perform single epoch photometry against our reference image. So we want to say quantitatively what is the same, what is different relative to our reference. And then we again have all of the same issues about distributing coads to the scientific public. But actually, in terms of a pure data volume space, transient surveys and time variable surveys can be a lot more challenging because now instead of distributing one n times m coad to everybody, your data set grows the more exposures that you take. And for a lot of people, they care about very short cadence exposure. So now you have this very large data set that you're trying to get out to the public in a meaningful way. So we're just going to talk about the last two because we've already covered these three in talking about coads. But I'm going to say that difference photometry can be both at a pixel scale. So what I showed up here, so where you have an actual imaging frame that's called your difference image. And it can also be done at a source scale, which I'll talk about in a second. But this is essentially doing matched, often point source photometry across different epochs. So pixel scale difference imaging is constructing difference imaging by subtracting your reference frame from your science frame. And then you look in the pixels of the difference image for sources that have changed. This can be for sources that are just changing, I should say that are changing brightness, but not position. But this is also a great technique if you're looking for things that are changing in position. So for example, if you're searching for comets, those move much, much faster and much more than things that are very far away, like quasars. So pixel scale difference imaging can be a great tool for picking out these comets as they move across your survey. You also have source scale. So this is from a catalog of known sources. You perform matched photometry on your reference image and your science frame. One subtlety that you want to account for here is that your single epoch data are all taken under different conditions, and specifically different seeing conditions than your reference image. So when you do your matched photometry, you don't want to necessarily plop down the same size aperture for your reference image and your science image, right? Because maybe your science image was taken under 2 arcsecond seeing and your reference image was all like 1 arcsecond-ish. So you're going to say, oh, my source is so much fainter now, but really what you're doing is missing half the flux from the source because it's more spread out in your PSF. So there's different ways to do difference imaging, but they all have the same underlying principle, which is you want to account for the changes in your observation to calculate quantitatively what the difference is between your reference and your science frames. So now I'm going to talk a little bit about tiling and survey strategy at the very end. So these surveys, or many wide field surveys, as their name implies, cover a very large area of the sky. Tiling refers to the pointing strategy observers use to image contiguous and overlapping areas of the sky. So first of all, why do we tile? Why don't we just go back to the exact same position on the sky every time? That'll give us the same depth, right? Because we'll have the same total number of exposures on any given position. First is to overcome detector non-uniformity. So we talked a bit at the front about variations across the field of view in the detector characteristics. Sometimes detectors can have hot pixels. Sometimes detectors can even have bad columns or rows where you don't see anything. So you don't want to come back to the same exact position because then your hot pixels and your kind of wonky pixels will be in the exact same place every time. You also want to tile to fill in your CCD chip gaps. So we saw this in practice with the HSC imaging at the top, but when you have a tiling strategy, this also allows you to fill in a uniform way the areas of the sky that you don't see in any single given exposure. And then finally, it gives you an opportunity to provide contiguous imaging across your survey area. So this is what we would like to do in the ideal case. We want to go to a single area of the sky and tile it very nicely where we have the same observation conditions. We reach the same depth for every exposure. That is not necessarily what happens in real life. So imaging surveys are often characterized by the depth, area, and resolution of the resulting coads. So you might have heard, for example, LSST single visit limiting magnitude will be this. Its 10-year limiting magnitude will be this. And it's great to have the single scalar value, but the reality of these surveys is a little bit more complicated, or a lot more complicated. So as observers, we can't actually control many aspects of exposure quality. So first, not all parts of the sky are visible in any given night. You might have a night where you have great conditions and you're like, well, I'd really like to go to my deep field. Unfortunately, it's down through the ground. So there's nothing I can do about that. I cannot observe that part of the sky. The imaging quality for a given exposure depends on observing conditions. So if you only have 4 exposures that go into a stack, and let's say that one of your 4 exposures is that terrible seeing, terrible transparency, it's much less deep than the others. At what point do you as a survey decide to go back to re-image that exposure versus move on and try to cover as much area as possible? And like as we've discussed previously, not all parts of the detector are equally sensitive. You might have field of view, bandpass variations, sensitivity variations. So all of these are going to go into resulting inhomogeneities in your final survey coverage. There's not a silver bullet to obtain a completely homogeneous survey at the end of your run. So I'm just going to leave it to say that deciding when to reobserve and where to go on a given night is a very crucial part of the optimization problem that will change a lot depending on your science case and depending on what you want to prioritize. So with that, let's talk a little bit about how survey strategy relates to image processing. So different science goals can have or want, need or want, different observation strategies. So to give you a few examples, faint galaxy surveys might want very deep coads over a relatively small part of the sky. If you're trying to observe magnitude 27 galaxies, you better have a lot of exposure time, right? On the other hand, short period variable surveys might want really high cadence observations for known interesting targets, or maybe over a large area of the sky, to try to see what is changing over a short time scale. Because if you're interested on something that's changing over a day time scale, if you go back and visit it every month, you're going to be severely limited in what you can say on shorter time scales. And then transient surveys might want to monitor very large areas of the sky to maximize the probability of seeing a rare event we can't predict the position of beforehand. So there's these kind of competing different scientific interests that shape how surveys are observed and how survey strategies are crafted. So our last discussion question, I would like you to discuss with your partner, if you were the sole decider of all LSST observations, what cadence and coverage, this should say what cadence and coverage would maximize your specific science goals? So don't think about the wider scientific community, just think about if I were the one that could decide everything in LSST we're doing, and I only want to do my science, what would my optimal survey strategy be? And then after that, I'd like you to talk a little bit, if you did do that strategy, what kind of interesting science might you miss out on? So I'm gonna give you, let's say 3 minutes to talk about this in small groups.
What's your science? We are looking for nova, so we need a really high cadence for that. We're taking images like every minute.
How do you do that?
Like you would your own? Yeah, we have a small telescope in New Mexico.
Oh,
Yeah.
you use your own.
Yeah. Condor.
That's specific. So you basically have.
Oh yeah. Well, it's not as powerful. I wish it was. But
I see.
yeah.
But it does whatever you need it for.
Basically. Yeah. So I guess the stuff that we're most interested in is the transient stuff, like a large area and like fast images. Or what about you? Are you more interested? I mean, I know you do spectra, but let's pretend it's everything.
Yeah, so I'm looking for like a binary. So in short time, I don't know if you take a lot of pictures, but I need in a long run how they change.
What
So
kind of
like
binaries?
black hole runs.
Okay.
Massive black hole runs. But like their separation distance is like somewhere sub 4-6 separation. So I don't think that you can see anything in the image, but in spectra you can see like blue shifting and reflection.
What is the period?
Yeah, so period, well, it could be very different, but like in the ones where you can see any change would be like 100. There are some with 100 days as well.
Yeah.
Or 200 days, which is less than a year. So if I get like yeah, or like one week a year. So I can do something. So I don't know how this relates to this one.
LSST should be good for that actually, because I think it's like, it's gonna be a couple of years. Is LSST gonna
But
be?
also like, yeah, I already have spectras for most of them from DESI, and then I will get new ones from LSST. Yeah, so that would be like my addition. And then for like some that are like really interesting to me, I also send them as like a secondary targets in the DESI collaboration as well, ask them to like observe it. So they usually do that. But yeah, I don't know how it relates, like which part it relates to.
Okay, let's come back together for our last discussion. And I would love to hear about your selfish strategies and what science we might miss out on if we were to adopt that for the whole of LSST. And I'd also love to hear from some people who we haven't heard from so far in the discussion. Does anybody want to go first? Yeah, in the back.
Yeah, I do supernova science, so I would more galactic plane. So the rolling cadence, I could see how this happens. But I would to have more consistent in all filters, or at least 4 filters, like on a regular basis instead of really prioritizing them. So right now, like RNG is prioritized, and then human flight was so much prioritized.
Yeah. For the people who don't work on supernova, can you say really quickly why having more colors would be so important?
Yeah, because we learn a lot about, so the temperature of a supernova and the radiation tells us a lot about like energy exposure, like the vast. And then also a lot of material around the star when it explodes after we turn. So like really early phase classification, having really precise information.
Great. And what interesting science do you think we might miss out on with that strategy?
With the mice just strategy.
Yeah.
So you're ignoring the galactic plane, so like all stars.
Yeah.
I can see if you want to prioritize like high redshift, like we're talking like high redshift galaxies, for example, it would make more sense to more heavily prioritize like the high wavelength bands.
Yeah.
More consistently. If you're doing more even distribution.
Yeah. Does anybody here work on the galactic plane? So what would your ideal strategy be, and what do you think we'd miss out on if we were to adopt that?
I would as short as possible, like even if it meant limiting the overall duration of the survey. If we had hourly, or like 6-hourly cadence, I think that we could determine a lot more about like the short timescale variability of stars as they're connected to rotational modulation. Same thing goes for supernovae. So it's like one very recent example of a supernova that shows 12-day periodicity after its explosion. I feel like we know that there should be a lot more supernovae like that. It shows some sort of periodicity, but it's also kind of the companion interacting with remnants. And I think if we had that sort of high conflict.
Yeah, if we adopted only high cadence observations, what do you think we might potentially miss out on?
No.
Nothing. It's a perfect strategy. Does anybody disagree with that?
No.
No, we should only do high cadence.
Infinite time resolution.
Infinite time resolution. What about area? Do you want very large area at low depth, because there's going to be a trade-off maybe between area and cadence.
Yeah, I think what we were discussing was like with the maximal slew speed that avoids breaking the telescope, like what is the fastest we can cover the entire sky?
So this is, if we wanted to commit to covering the entire sky as often as possible, does anybody have science that would not benefit from just full sky coverage at the expense of depth over small area? Yes, in the back.
High redshift galaxies. Exposures in a very small area. Exposures, but some.
Yeah, so your ideal would be long exposures on a very small area of the sky to get at these very faint high redshift galaxies. Yeah.
So the diffuse galaxies that may not be like us, are far from us, but they have things.
Yeah, that's another great example. So low surface brightness galaxies, again, very faint. Again, we need to get deep to see them. But again, that also limits how much area that we can cover. So this exercise is just a demonstration of how we have a lot of diverse science goals, and not all of those science goals can be optimized with a single survey strategy. So I won't really get into this because I'd like to move on to the problem set, but this is just a schematic of the LSST baseline survey. And you can see a lot of the features that we were just talking about popping up, right? So we have the wide, fast, deep survey over a large area. We have some mini micro surveys. We have deep drilling fields, so going really deep on a small area of the sky. I don't think anybody really talked about this, but also target of opportunities. So if you see something very interesting, go there immediately. But really this discussion is just to underscore how we have a lot of different science to do, and we have a limited amount of resources to do it. But if we tile and stack and co-add and difference in the right ways, then we can try to maximize our scientific output for these data sets. So I would like to take a really quick break if we have time before we move into the problem set. So let's take a 5-minute break before we move on.
Very short, very
So CO is the first priority.